So now let's go through the practice problems for arithmetic. So the first problem here was about signed magnitude. So I gave you a bunch of 4-bit signed magnitude numbers and asked you to calculate the answers and show it to me in decimal. So remember, in signed magnitude, the first bit tells you if it's positive or negative. So this is a negative number because the first bit is 1, and this is a positive number because the first bit is 0. Then I asked you if you could use regular binary addition for these or if you had to do something special. So let's go ahead and walk through these. So the first one we had plus 3 minus negative 3. Well, this is plus 3, it's 2 plus 1, and the sign bit is not set, so it's positive. And this is minus 3, it's again 2 plus 1, but the sign bit is set, so it's minus 3. So we have plus 3 minus negative 3, which is plus 6, and plus 6 is going to be 4 plus 2, not plus 1, and then the sign bit is not set because it's positive. And we can go through the rest of these. This is plus 3 plus a negative 3, which is going to be 0. This is minus 3 minus a negative 3, which is going to be 0. And here we have minus 3 plus a negative 3, which is going to be negative 6. And here's negative 6. You can see it's the same thing as what we had as 6 before, but we just changed the sign bit. So with a 0, this is plus 6, and with a 1, it's negative 6. Now the second question was, using signed magnitude, could you use binary addition for these? So let's take a look just at the first one here. So binary addition doesn't work. If I just put these together in binary addition, I get 0, 0, 1, 1 plus 1, 0, 1, 1, which is going to give you this other number here, 1, 1, 1, 0, and that's not what we want. This is the answer we wanted to get out of it. So binary addition did not work here. You had to be careful about the signs and which way you added them in order to make this work, and that's what you did in your head when you converted them from decimal, figured out what the answer is, and then went back to binary. So this is a big problem with signed magnitude. Doing subtraction requires that you be careful about what order you do things in and what's negative. The next slide was about 2's complement. So start out, let's just convert these numbers into 4-bit 2's complement. So to get started, plus 4, well, that's going to be 4 plus 0 plus 0. So just set the bit that corresponds to 4. Minus 4, so for minus 4, for negative numbers in 2's complement, we know we're always going to have a 1 in the most significant bit. So how do we make minus 4? So for minus 4, we can make it from plus 4. So here's our plus 4. And remember, to make it negative, we invert and add 1. So 0, 1, 0, 0 becomes 1, 0, 1, 1. And then we add 1. When we add 1 into here, we're going to get 0 with a carry and go through. And we're going to get 1, 1, 0, 0. So this is minus 4. And let's figure this out. So this bit right here is minus 8. So this is minus 8 plus 4. And minus 8 plus 4 is negative 4. Now let's figure out negative 8. So negative 8 is the smallest negative number we can have with 4-bit numbers. So this is just 1, 0, 0, 0. This is negative 8 plus nothing. So negative 8. How about positive 8? So positive 8 is a problem because the largest positive number we could get is if we don't set the first bit and then we set all the rest to 1. So this is 4 plus 2 plus 1, which is 7. So the largest number we can represent with 4 bits 2's complement is 7, so we can't represent 8 here. Now let's take a look at doing subtraction in 2's complement. And we'll see how you can use the same approach every time. So I gave you this number I wanted you to subtract in 7 bits 2's complement, 8 minus 12, and I told you to remember the formula here. In 2's complement, a minus b is a plus not b, so we invert b and add 1. So let's take a look at this. So a in 2's complement is what? Well, it's 8. So here's 8 in 7 bits. It's going to be all zeros and then 1, 0, 0, 0. So this is the 1's place, the 2's place, the 4's place, the 8's place. So this is 8. Now what's b? So b is 12. So 12 is just going to be the same as we've had before, 8 plus 4. So this is the 1's place, the 2's place, the 4's place, the 8's place. This is 8 plus 4 is 12. Now we're going to go ahead and invert b to get not b. So we're going to change all the zeros to 1's and vice versa. So here we go. This is not 12. Now in order to make it negative, we have to invert and add 1. So we're going to add 1 to this here. So we take this and add 1. When we put in the 1 here, we're going to get a 0, and we're going to get a carry and 1, and we're going to go through. And here's our value coming out. Now let's go ahead and convert the final result. So we had the 8 plus not 12 plus 1, which gave us this value here, plus the other value we had from the second part here, which is going to give us our final value. And this here should be the result of 8 minus 12. So now let's go work this out and see if it gives us the right answer. So what is this? Well, it's minus 64 plus 32 plus 16 plus 8 plus 4, and then these are zeros in the 2 and the 1 place. So if you work that out, that's minus 4. and that does indeed give us the value we expected. You'll notice I have an error here. This 1 should be moved over one place. So now let's talk about overflow in 2's complement. And remember, overflow was a little trickier than when we had in regular addition. So let's work this out for a few of these problems here. So here's our first result here, and we're doing a subtraction. So how do we convert a subtraction to an addition? Well, if we want to subtract 1100, that's the same thing as adding negative of this value. To make that value negative, we're going to invert and add 1. So we take our 11000, we invert it and add 1, we get 00111 plus 1, which gives us 0100. Okay, so now let's go ahead and do the addition. So now we've got this value here plus this value, so the same thing as the subtraction. So we go ahead and we add these two things together, and here's our result. So let's take a look at it. What's the carry into the sign bit? Well, the sign bit's the most significant bit, and it went from 0 to 1, so the carry in is 1 here, and the carry out is 0. We didn't have our next value set to 1. So this carry into the sign and the carry out from the sign are different. So yes, this does overflow. And let's take a look at the decimal. So this was 8 minus negative 8, which is plus 16. The largest value that we're allowed to have in a 5 bits 2's complement number is plus 15. So it's not surprising we overflowed. We can't represent this value. Let's try the next version here. So when I go ahead and do this addition, here's the results I get here. So the carry into the sign is 0, the carry out from the sign is a 1. So I didn't have any carries going in here, and I had a carry going out. Why didn't I have a carry going into the sign? Well, look at the addition here. In the place right before the sign bit, I was adding a 1 and a 0. And 1 and 0 gave me 1, but it didn't give me a carry. So I didn't have a carry in. So is this going to overflow? Yes, it's going to overflow, because the carry out from the sign is different from the carry in. Here's my carry out. I added 1 and 1 together before, which gives me a 0 with a 1 coming out. So what's the decimal version here? Well, this is minus 16 plus negative 1. So this is minus 17. But the smallest value I can represent in 5 bits 2's complement is minus 16. So I overflowed. Let's take a look at this next one. So here we're going to go ahead and add these numbers together. And what do we get? Well, the carry into the sign is 0, as we're adding a 1 and a 0. And the carry out from the sign is 0, because we're adding a 0 and a 1. So we didn't have any carry outs. So does it overflow? No, because the carry into the sign and the carry out from the sign are the same. So what is this in decimal? This is minus 16 plus 15, which is minus 1. And minus 1 can be represented in 5 bits here. It's represented exactly this way, 1, 1, 1, 1, 1. So we didn't have an overflow here. Now let's take a look at fixed point values. So here we have a bunch of different fixed point formats, 6.1, 2.2, and 2.5, and let's figure out what the maximum and minimum numbers we can represent with these values are. Sorry, with these formats. So for 6.1, the maximum value is 11111.1, and this is 31.5. So this is 16 plus 8 plus 4 plus 2 plus 1 plus a half, which is 31.5. Now the minimum value is going to be if I set all these first ones to 0 here. So 0000.1, and this is just a half. So with a 6.1 format, I can represent numbers from 31.5 down to a half with a precision of 1/2. Let's take a look at this 2.2 format. So the maximum here is also 11.11, so all ones. But now we interpret this differently. This is 2 plus 1 plus a half plus a quarter, or 3.75. The minimum value is also going to be if I do 0, 0, 0, and then a 1. So 0, 0, 0, and 1 is now 0.25. So this is just a quarter that I add in here. Now how about this 2.5 format? Well, the maximum here is 11.1111, set them all to 1s. And this is going to be 2 plus 1 plus a half plus a quarter plus an eighth plus a 16th plus a 32nd, which is 3.96875. So this format can get almost up to 4. And the minimum value we can get is, well, all zeros are the 1 here. The smallest value is a 32nd. So now you can see, depending on where I put this decimal point, I can get very different maximum and minimum values and different levels of precision. So now let's talk about floating point here. So here I've given you some numbers in a floating point format, and I specified the format up here. This is a sign bit, and then we've got our mantissa, and our exponent is specified as some value minus 4. And we're going to go figure out what the decimal version is, and then we're going to discuss whether this is normalized to a format which had an implied 1 on the mantissa. So it assumed that there had to be a 1 there for it to be normalized. So let's take a look at the first example here. So I've gone through and color coordinated these based on what parts they are. So what's the decimal version of this? All right, so we've got a 1 here, so that means we're going to have 1 times negative 1 out front, so we're going to get a negative 1 here. And then here's our mantissa, so 0, 0, 1, 0, 1 in here, and here's our exponent, which is 6. So this is the number we have. It's negative 1 times 0.0101 times 2 to the 6 minus 4, which is 2 to the second. So 2 to the second here means move this over 2 decimal places. So this is the value we get, negative 1 times 1.01. So this is negative 1 times 1 plus a quarter. So this is the quarter place, so minus 1.25. So is this normalized? Well, for this to be normalized, I need to have this implied 1 here. So to normalize this, I'd have to take this mantissa and shift it over 2 places so that 1 was over there. So to normalize, I shifted to the left 2 places, and this is what I get. I shifted this over to the left 2 places. Now over here, I need to make sure my exponent is 2 smaller. So instead of being 2 before, I need to make sure it's 2 smaller, so I want to put in a 0 here. So I need to reduce my exponent by 2. And this is what I did when I reduced my exponent by 2. Here the exponent before was 6, now the exponent's 4. So this here is the normalized version of that number. Oh, I'm sorry, this isn't the normalized version. The normalized version would have, sorry, no, this is the normalized version, my mistake. You don't see the first 1 here. You see what happened with my mantissa here is I shifted it over, but I don't keep the first 1 in the representation here because there's an implied 1. Let's take a look at the next value here. So here I've got my mantissa, it's 1, 1, 1, 1, and I've got my exponent 1, 1, 1. This is going to be 7. So here's my value. I don't have a sign bit here, so it's going to be positive 1 times 0.111 times 2 to the 7 minus 4. And so what's this going to be? Well, 7 minus 4 is 3, so we're going to shift over the decimal place over 3 points, and here's our value. Plus 1 times 111.1, so what is this? Half plus 1 plus 2 plus 4, so this is 7.5. Now, is this value here normalized? Well, it's not normalized because normalized assumes that we have a 1 before the binary point. So we need to move it over by 1 to do that. So to normalize this, we have to shift it left by 1, and here's that. So to shift left by 1, I take the exponent, I make it 1 less, so instead of having 7 here, I just have 6. Now let's take a look at the last example here. So this example is positive because we don't have a sign bit, and it's 0.0001 times 2 to the 0 minus 4. So this is now a negative exponent, negative 4. That means to convert this number, I need to move my decimal place 4 points over to the left. So here's the number I get. 1 times 0.100000001. So I took this value and shifted over 4 places, which is 0.0039. Now, how do we normalize this? Well, to normalize this, I need to shift this over 1, 2, 3, 4 places. So I need to shift it to the left 4 places, but I can't do that. Because in order to shift this over to 4 places, I need to get a plus 4 over in the exponent, but the maximum value I can get my exponent is 7 minus 4, or 3. Because remember the format I have up here, it's these 3 binary digits minus 4. If I make all these 3 binary digits as large a number as I can, 1, 1, 1, and I subtract 4, I've got 7 minus 4, the most I can get is 3. So this number is a number that you can't express in a normalized format.